To help you understand how to write code within this event-driven paradigm, I've written a really simple flight plan in a program called upanddown.py. And I'm going to show you that code in just a second, but first I want to show you what that code does. And the name might give it away. But if I run upanddown.py, you can see the rotors start to arm, the drone takes off, flies back down, and then turns off. Now, this was a very simple flight plan, but let's take a look at the event-driven code that actually caused it to happen. So here is upanddown.py, and as you can see, it's just over 100 lines of code, which may seem kind of verbose for how simple it is, but this verbosity actually has a reason. So let's talk about how this code works. At the top, you can see there's a lot of imports, as is often the case with a Python file. We can ignore those for now. Likewise, with this phases class, we don't need to pay too much attention to it just yet, though we will shortly. And then there's this upanddownFlyer class. And it inherits from this drone superclass. This is Python notation for defining a class and saying what the superclass is. And this drone class is something that we're providing for you, and it's really pretty powerful. It's got a lot of high-level commands that allow you to control the position of the drone. It lets you set different waypoints and other sorts of high-level commands like that. You'll be using this class throughout the nano. But let's not worry about all that just yet, because for now I really want to focus on this initializer, or the constructor for the class. And let me just walk through line by line really quick how this initializer works. So first, we call the superclass initializer. This is pretty standard. Next, we've got this boilerplate. This target position is going to be used by the superclass to navigate to different waypoints. And also there's some logic checks in the superclass drone that only begin flying if the drone is declared to be in a mission. So we need to set this to true. Again, I want to ignore this flight phase stuff for now and really focus on what's similar to that chatbot code you just saw, which is this callback registration part. And as you can see, this looks almost identical to the chatbot code. We're calling a function. It's called register callback. It takes a message as a first argument, and then a callback function as a second argument. So what this line of code is saying is anytime we get a local position update from the autopilot, we want to call this function local position callback. And we've got something similar going on when we get local velocity updates or state updates. So from a high level, you can see this code is actually pretty similar to the chatbot, since during initialization, we just register particular callback functions to certain events or messages. Now I'm going to peek into this local position callback in just a second. But first I want you to think about when this function is called and what it's responsible for doing. Since I'm registering this function to this local position update, well, I'm going to be getting local position updates from the autopilot many times a second. And most of the actual waypoint following logic is actually handled in the drone superclass. So what this function is responsible for doing is implementing any logic that's particular to this particular flight plan, going up and then going down. Since going up requires going up until we reach a certain target altitude, that's what I have to check for in this callback. So let's see how that's implemented. And as you can see, this flight phase stuff is showing up again. And this is probably starting to make a little more sense now. If the flight phase is the takeoff phase, well, that's when we're performing this altitude check. So the first thing that happens is this coordinate conversion. And this is a little funny. What's going on here is there are two different coordinate systems that are trying to play nicely together. And for one of them, the altitude, the z-axis goes up for positive, and for the other one, the z-axis goes down for positive. So we're just making a little correction there. And then the interesting logic happens down here, where we're checking to see if the altitude is greater than 95% of the target altitude. And if it is, we begin this landing transition. And really, this is sort of how we're going to think about how flight works in this event-driven paradigm. We've got these callbacks, and depending on the state we're in, we do some logic and then perform state transitions. So hopefully this event-driven portion of the code is starting to make some sense. The other thing that's important to understand about this code, and which we're going to be working with shortly, is this idea of phases or states. Once you get a sense for how these phases and these callback functions, messages and transition functions all interact with each other, you'll be able to start implementing your own flight plans that play nicely within this whole event-driven framework. So now I'd like to look a little bit more into this phases class.